Okay, so this is video 4 of lecture 6, structural analysis, and this video is looking specifically at frames and machines. So it's beginning kind of slide 36-ish in the lecture 6 PowerPoint. So you'll see a couple of slides further on. First couple of slides you've got some example photographs. But then you get the definition of a frame or a machine. So a frame is something that is supporting an external load, whereas a machine is something that has moving parts, so it can move an external load about, it can change its position to change the support that it's offering, that force, that load, and it can change the forces that are supporting it. Really what we're going to do is we're going to look at a couple of examples, and it's really real-world situations of structural analysis and what's actually happening in those structures. So I'll start with the example on slide 41. I'll draw it and then we'll solve it together. So this is the diagram of the question from slide 41, and we're asked for the horizontal and vertical components of the pin reactions at C and the magnitude of the reaction at B. Well, you should notice that AB is a two-force member. You've got a force at either end, so we can recall that the resultant force will be acting along the line that that connects A and B. We know that that's 1 metre down there and it's 1 metre across here, so we've got an angle of 45 degrees in each section there. So that'll be useful for later, so we can now simplify this onto a free body diagram. So our free body diagram, we can simply put our force in there, and that's going to be 45 degrees in there as well. And we've got the 800 Newton meters turning moment, and we've got the 400 Newton force, and we've got the distances here of 2 meters, 1 meter, and 1 meter. That was there to there, that was to the end, that's to the bottom. So that's our simplified free body diagram. We've also got forces at Y, we've got forces at C, we've got a CY and a CX. The first thing we do, well, the easiest way, I need to call that FB, don't I? The easiest thing to do first to ignore our two unknown C forces is to take moments about C. So if we take the sum of our moments about C, that's going to equal FAB sine 45 times 1. So that's going to be that force times 1 metre, because it's 1 metre from C. So FB sine 45 times 1 minus FB cos 45 times 3. So that will be this component here, and it's 3 metres perpendicularly from C. We've got plus, it should be 45, sorry, we've got a plus 800, which is a moment that's already given, and we've got a plus 400 times 2, which was the force that was given to us, and that all has to equal 0. We can then rearrange that and we can find FB to equal 1,131 newtons. So that gives us FB. We then go on and we can find the support reactions at C using some of the forces in the X and the Y direction. So our sum of our forces in the X direction, based on the assumptions we've made, are going to be minus CX plus 1131 sine 45 equals 0. So CX equals 1131 sine 45, which is 800 newtons. Similarly, forces in the Y direction, we're going to have minus CY plus 1131 cos 45 minus 400. You don't have to do anything with that moment because it's a turning effect. It doesn't give you a force in either direction, so you don't need that. And we can rearrange them because Cy is equal to 400 newtons. So that's a relatively simple example. There is a slightly more complex example for you to have a go at beginning on slide 46. So if you have a go and then come back to the video and I'll show you how to solve it. So this is the image from slide 46. Apologies, it's at a slightly funny angle. But you're asked to find the reactions exerted by the pins on the frame at B and at C. So a little bit more complicated, and you've got two different bits you're going to work on here. So you can break this down into those two sections. So the first one we'll focus on is just the slanting section. The slanting section, AC, we're going to have we've got a pin at the bottom, so we're going to have AX, and we're going to have AY. We're going to have 50 kilonewtons acting, and we can work out the distance, the horizontal distance, or the perpendicular distance there. That's going to be 3.5 metres, and we know that because the length here, hopefully you can see that, is 4 metres. The radius of the wheel is 0.5 metre. So we know that obviously this isn't the scale, but we know that the distance to the rope, from the rope to the pin, is 3.5 metres. We also know we've got forces at C, so they're going to balance, or try to balance the forces at A. So we've got a CY and a CX. We also know it's 6 metres there, and we know it's 8 metres along the bottom. So the first thing we can do is we're going to need some equations to try and solve. So if we to ignore the moments at A, to ignore the forces at A, we can do some of the moments at A. So sum of our moments at A is equal to minus CY times 8. So that's CY, it's 8 metres away, and it's minus because it's trying to turn it clockwise. We've got plus CX times 6, that's here, and it's 6 metres away. We've got plus 50 times 3.5, and that's obviously your the force of the rope, and that's plus as well because both of those CX and the 50 newtons are going to try and turn that structure anti-clockwise. That equals 0. Clearly you can't solve that yet. We can also do sum of the forces in the x direction, and that's just going to equal CX minus AX equals 0, so we know obviously CX equals AX there. And we can do sum of the forces in the y direction is going to be 50 minus AY minus CY equals 0. So there's not a lot you can do yet with that. So now what we'll do is we'll jump onto the new slide, and we'll look at the other piece, BC. Again, I'll draw it and I'll come back live. Okay, so here's our free body diagram for the second part for BC. The thing that you'll note here is I've got 2 metre measure there. It's 1.5 metres to the top of the to the middle of this pulley, which I haven't drawn on. Pulley, and then another 0.5 metre from the middle to the outer radius. So to the rope with the force, it's 2 metres total. Some other labels that I've missed off. We've got 4 metres there, and we've got 4 metres to the end there. And you'll notice that CX and CY are going the opposite way because we're looking at the effect on the other member, BC, not the member AC. So first thing we can do, we're not if we're looking for, if you remember in the previous equation, we've got 3 unknowns. We've got cx, cy, and ax. Well, we can get more equations with cx and cy in, and then start to solve them simultaneously if we take the moments about b, because then we can ignore everything that's happening at b. So if we do the sum of the moments at b, that's going to equal minus 50 times 2, and that's going to be from this force times this distance that I've already drawn in. We'll go, and it's turning clockwise, so it's minus. We're going to have minus 50 times 3.5, and that's from this force and this distance, and that's minus because it's trying to turn it clockwise. We're going to have plus cy times 8. Fairly obviously that's cy, and the 8 is the 2 4 metres added together. And that all adds to equal 0. Cx is working straight through the b-axis, so Cx is straight through the b point, so b times 0 metres, so we can ignore it. Well, we've only got one unknown there, so we can rearrange and we can say Cy equals 34.4 kilonewtons. Well, now we've got that, we can go back and some of our moments about A has only got Cx and Cy in, so if we substitute Cy into our sum of our moments about A from the previous slide, we can get Cx to equal 16.7 kilonewtons. And then finally, we're asked for the forces in B. Well, if we focus on member BC that we've drawn here, we can do the sum of the forces in the X and the Y. So our sum of our forces in the X direction is going to be Cx 16.67 or 16.7 plus the 50, which is the horizontal part of the rope, so this bit, minus bx, whoops, I've stayed in orange, equals 0. So bx equals 66.7 kilonewtons. And the sum of the forces in the y direction is going to equal by minus 50, and that minus 50 is that part, plus 34.4, and that's your Cy, and that all equals 0. So By is going to be 15.6 kilonewtons. So that is just one example of putting everything we've done together. So we've got the different support joints, considering things in larger structures and considering those structures and analysing them at the joints, and concludes the lecture 6 on structural analysis, particularly video 4 on frames and machines. So just to recap, a frame is normally a stationary object that supports a load, whereas a machine is something that can adjust itself to change the force that's supporting that load and maybe move that load around. There are lots of practice tutorial questions on these, again on the website.